you very much. So to the students out there, welcome to hearing a little bit about the School of Materials Engineering. Materials Engineering is a major. I'm Professor David Barr. I'm the head of the school, and I have the good fortune to also have been alumni doing my undergraduate here back in the late 80s and early 90s when we didn't do this online. So I'm going to tell you a little bit about what our students do on career paths and where they go. I am joined by 6 MSc students that are our school ambassadors. And after my presentation, we will open it up to small breakout rooms where you can ask them real questions about the real guts of the materials and what it's like being an MSc student. You should always try to trust the people that look a lot more like you than me right now, right? Because we think we know what happens and they know what really happens, okay? So with that, we're going to go ahead and get started, and just wanted to give a little plug for our slogan, and that is, you can't make it without materials. And that's, we think, a fun way to say that. So a lot of times people ask, what is material science and engineering? And it's a relatively small discipline. I am going to go out on a limb, and without knowing who you all are, I'm going to guess that at probably on average, half of you didn't know what this was before you got to Purdue, or didn't even know it existed. So we make the stuff that other people make things out of. And that means sometimes we design new materials that let you build something new. We also modify or improve existing materials. We develop processing methods so that you can make those materials more efficiently. And efficiently is usually good in terms of its lower energy use. There's good from a holistic sense. It's also good from a cost sense. We also work on why materials fail and analyze how things perform under harsh conditions. The kind of thing that you wish somebody at United and Pratt & Whitney would have done a few weeks ago. Okay, so just to give you a few minutes, we found it helps if you think of us as real people and not just professors. So I did my bachelor's and master's here at Purdue, as I mentioned, back in the late 80s, early 90s. I moved up to Minnesota for my PhD in materials science. During that time, I spent some summers out at Sandia National Laboratories that was in the California operation. I won a PCASE Presidential Early Career Award for Science and Engineering from the work I did there and at Washington State University, where I became a faculty member. So I joined the School of Mechanical and Materials Engineering at Washington State. For those of you that don't know where WSU is, I usually ask, you know where Seattle is? And people say yes. And I say, go as far away as you can from Seattle and still stay in the state. So we are 8 miles from Idaho. So not Seattle. The good side of the state, not the wet side that's crowded. I became the director of undergraduate research for the university there, and then I became the department head for the School of Materials and Mechanical and Materials Engineering. And back in 2012, I moved here as the department head. So, and to let you know what I do in materials, other than talk to first-year engineers and teach classes, and I do research, like all of us do at a research institution. And what I do is I study the behavior of small materials, and some things we test small because the thing is small, and others we test small because we can characterize it well at that scale. And so a lot of times if you look at, why don't we operate materials at higher temperatures? What goes wrong in an engine if you're trying to operate at a higher temperature? We want to work out, how do you tease out properties as in harsh environments? And it's a lot easier to do that on a small piece of material than a really big piece of material. And the other thing is sometimes a really big piece of material, like something that's down in a nuclear reactor, is a lot safer if you're handling a really small amount of it than a really big piece of it. Okay, and so if you design materials, what you would like to do is you would like to test while you can still make changes. So computationally, we do simulations that allow us, there we go, that allow us to simulate individual atoms. That's great, but it's hard to move and process individual atoms. You can also go all the way up to building a plane, and it's really expensive to wait to build a plane and then test it and see, did that work? So you would like to perform your tests where your experimental tests and your computational simulations match up. And that's on the scale somewhere between hundreds of thousands of atoms up to billions of atoms, but not trillions and more of atoms. Okay, so we tend to work on that small scale mechanical behavior area. And just some as examples, we look at a material here. This is growing an oxide on titanium or stainless steel. This particular example is titanium. The reason titanium is so corrosion resistant is it forms this really nice oxide. Under certain conditions, that oxide mudflat cracks. And what we've done in this case is we use those cracks to actually store peptides that are antimicrobial so that we can have a titanium surface that emits material that kills Listeria bacteria. So we have a way that your titanium kills the thing that gives you Listeria. It's kind of nice. We also test materials that are hard to handle when you go to large volumes. And I show here two energetic materials. Energetic is a polite way of saying explosive. RDX and TATB are two materials. RDX is the material that ends up in C4. And this is a project we had with Los Alamos where they wanted to study the deformation behavior of these particular these particular materials. And then we looked for simulant materials that captured all the properties except the blowing up part so that they could train their technicians who actually have to learn how to machine things that explode. They could get practice without having to worry about blowing their hand off. Okay, and so what materials engineering does is we work somewhere in between atoms and aircraft. Okay, so if you're into designing the chemistry and yield of a particular reaction and how these two bonds break and what's my efficiency of that and what's the yield and how that reaction goes forward and back, MSE is not really for you. That's more chemistry. And if you want to design the shape of a new plane, yeah, it's not really our gig either. So if you want to design the composite materials used in the plane, if you want to test the composites, and if you want to develop how that composite fiber interacts with a polymer and how that relates to the underlying strength of the material, that's what materials do. So we work bigger than atoms, smaller than aircraft. Okay, so you can design materials, you can make them more efficiently, you can lessen the environmental impact of those materials. Several materials that we rely on in a day in and day out basis, to be honest, are not the friendliest things out there. The people of Flint would probably say that a material that was really good for sealing up pipes may not have been the best long-term solution for human health. So we work in teams that do product design, and we do selection materials for those. We have alumni that go out and work for government agencies and teaching, and we have people that do failure analysis and testing validation. Okay, so people in materials go to other fields. So there are companies that do materials and just make materials, and about a third of our alumni go off into fields where they make the stuff that everybody else makes things of. But you see people going into aeronautical for ceramic coatings on jet engines and hypersonics. You see people going into civil for drilling cements and fracking. You see people going to mechanical who design carbon fiber that gets used in composites, BME for aerogels, chemies, materials people work on designer emulsions. We have people that are doing drug encapsulation in the pharmaceuticals, people that work on lead-free solders. You may have seen the big announcement that Purdue is leading up a $40 million Department of Defense project to get lead out of solders in the military applications. And that's led out by us. You have people that are in environmental engineering for clean water technology, nuclear, ag and bio, and IE. So materials people end up interacting with all these other disciplines. So there's not one particular typical thing that stands out where all materials go to this. Nope. What we end up doing is finding out materials are everywhere, and our students therefore follow a similar path. Okay, so if you look at something as, we like to take simple examples. So you go to a bicycle, and to be honest, 130 years after that original bicycle picture is shown, the current bicycle does not look that different, correct? But one of the big changes has been the materials that it's made out of. So the weight of a bicycle changes significantly. But of course, we know how to make lighter bicycles. We knew how you could have made a lighter bicycle in 1890. The problem was if somebody my size had sat on it, it would have buckled and crushed. Right? So it's not just the strength of the material or the stiffness of the material, but it's things like the stiffness to weight ratio or the strength to density ratio that helps us drive design advances in material systems. And so that might be in how do you do things for aluminum recycling? And how do you pick alloys so that the components you put into the aluminum can be efficiently put into other products? So how many of you know, and of course, because I can't see you, I'm going to assume you're all raising your hand. How many of you know there are actually 3 different aluminum alloys in an aluminum can? So if you go to recycle your aluminum can, you cannot turn it back into an aluminum can. Everybody's hand went up because that's well-known knowledge, right? No? Shocking. So how do you handle the fact that the recycling stream for aluminum cans is actually not an aluminum can because you had 3 different alloys to start with? We have people that work on organic semiconductors for flexible electronics. We have people that are really focused on water splitting. If you're going to have a hydrogen-based economy to reduce carbon footprint on transportation fuels, how do you do that in an efficient way? And we have folks working on things like how do you put copper onto masks and act in an antimicrobial, antiviral way. Okay. We also look at things that go wrong. Okay. And so if anyone remembers, well, okay, there's not a single person on this call that remembers, but you may have seen the story about the Aloha Airlines flight in 1988. So this is a case where basically the top third of the plane popped off during flight. There was a fatigue fracture that occurred. Unfortunately, one person lost their life. That one flight attendant who was up at the time that this occurred. Everybody else landed safely. So it's tragic that somebody died, but it is a case where we know why materials fail like this. Every time a plane lands and takes off, if you remember back in the days when we used to fly, they would say the cabin is pressurized for your convenience. That's right. They take the plane and they blow it up like a balloon so the pressure around you feels comfortable. The challenge, of course, is every time you take that riveted aluminum structure and you blow it up and you let it come back. You blow it up and you let it come back. That's a cycle, and deformation occurs that can lead to fatigue cracks. And so materials people look at analyses of understanding how materials deform and how they last in harsh environments. Okay, now a little bit about the field as a whole. So we are a relatively small discipline. So we graduate somewhere in between 50 and 70 students a year. And if you put that versus the other departments around here, this was 2018, 2019, just to let you know. Next year, I think Aero is going to be almost as big as ME. ECE has gotten smaller, but you see, we're one of the smaller schools. But it turns out we're also the biggest school in our relative footprint within our discipline. So nationally, there's only about 1,800 materials engineers a year that graduate. Does anyone know how many first-year engineers there were here at Purdue this year? No? No? Anyways, 2,400 or so. So we brought in more engineers to Purdue than the entire country outputs in materials engineers. So we put out about 3% of the nation's MSEs. We're a relatively big footprint in our field, but we're still a relatively small group of people on campus. We're about 35% women and about 12% underrepresented minority students at our undergraduate level. And our graduate level stays similar in terms of gender. We were ranked 11th in US News and World Report undergrad. The 2 schools in front of us are Penn State and Carnegie Mellon, and we're coming for them next. Our graduating student to faculty ratio is about 2 to 1. So that puts us about 3 times more interaction with faculty than you get in the other departments. And that can be a good thing, which I'm sure the students will all tell you, or it can be a bad thing, which I'm sure the students will all tell you, because if you try to hide, we know who you are. We are expanding our co-op options. So we have students that do everything from 3-semester co-ops 5-semester co-ops, integrated 1-year co-ops. We've been doing that for years, and those options are available. We have some, we've won, our students from MSE have won the business plan, the Burton Morgan business plan competition a couple times. And we work on all kinds of materials: metals, ceramics, polymers, composites, electronic materials, green materials, biomaterials. So basically we make stuff, and there's a lot of stuff out there. We come from, we're a state school, but we're not just Indiana. About 60% of the MSE students are from out of state. Our neighbors to the left and the right are our largest contributors, but we hit pretty much, most of the US, and we have about 10% international undergraduates from 7 different countries. When I say we make stuff, that means you're going to spend time in labs. Labs are an important, crucial part, and even this past semester, I think some of our students will say, hopefully they will back up, you're still in the lab doing stuff, you're just not doing it in groups of 1, 2, 3, 4, 5. That room can only hold 4 students, so there's 3 students and a TA at a time in that lab right now. So we have people working on things that might be, MSE 235, they're doing solidification, they're doing mechanical testing. We have a lot of students doing undergraduate research, and we have some students doing some outreach. About half of our students do undergraduate research before they graduate, and our co-op program, between co-op and summer internships, about 75% of our students have done an industrial term before they graduate. So like I said, we allow up to, part of the reason we have so many students doing undergrad research is you can count up to 2 classes, so 6 credits of research as technical electives. And we have students who start as early as the summer after their freshman year, most years. This year, maybe not so much. We do have some study abroad opportunities. Imperial College is our most popular one. Then we have some short courses that have happened in Brazil, China, and Spain. And then two of the Goldwater Fellows, which is one of the most competitive undergraduate research fellowships in the entire country. It's a national competition. No school can ever have more than 4 a year. Past 5 years, 2 MSEs have won it. So we're doing better than our fair share in that. Now, we think research is important, but we also think industry is important. And so 100% of our students have to do a funded undergraduate senior design team project. These are 1-year projects, and they're real problems from industry. And you have to partner with the industrial engineer, the engineer in industry, who helps guide you with your advisor to solving a problem. And I am sure that some of the students will tell you about their senior design project if you end up in those breakout rooms, where they're working for companies that may range from Arcelor, now Cleveland Cliffs, Cummins, Medtronic, small businesses like IBC, government agencies like the Air Force, polymers, companies like Bueller. So it's across the board kind of projects. Okay. The other thing the message I want to leave you with is we don't have anything that's normal. So about 70% of our students go to industry, about 25% go to their 100% paid graduate programs, and about 5% are still looking. If you don't believe me, I recommend you go to CCO's website, cco.purdue.edu/data, and you can look up where everybody goes from different majors and what the 5-year trends in employment are. And you'll see that we're pretty consistently sending about 25% to grad school, and then about, that 2/3 industry, and then the balance still looking. Manufacturing, aero, automotive, health, and pharma. Last year, I think of our graduating course class of about 60 students, about 15 went to grad school. Of the remaining 45, they went to 42 different companies. So there's no normal. It's up to you to figure out what you want to do, and you get to do that in a major that is small enough to have a lot of interaction, but yet big enough to have the resources to try lots of different things. Okay. And so that's where some of our folks go. One of the features that we do is we do a seminar series for our undergraduates where we bring alumni back to talk about career advice and options. And this year we've had speakers that are coming anywhere from Seagate. We had somebody at AMD and Dell yesterday. Today we had somebody from NASA, Langley. She works on materials for wear-resistant coatings to keep moon dust out of rocket nozzles so that you could take off again once you launch better. And then let's see, Friday we have a speaker from Nike. So that's a pretty broad swath. AMD and Dell, NASA, and Nike. And what do they have in common? They all work with materials. So we got some people that work at Procter & Gamble. I want to show you a short video. This should take 2 minutes, I think. And so I'm going to hope this launches. And I need to share the video. Can you guys see the video? I need somebody to unmute and say yes.
Yes.
Okay.
Hi, my name is Sarah, and I'm a materials engineer for Bridgestone Americas. Being in product and development, I work in between research and manufacturing. I work on both bringing in new technologies into mass production while also improving upon our current and existing products. Materials engineering for tires has 2 specific categories. We have our reinforcing materials and our rubber compounding materials. For reinforcements, we have different fabrics, nylon, polyester, rayon, things like that. And we have our steel components, which are plated in either brass or bronze to help adhere to our rubber components. The whole purpose of our reinforcement materials is to provide durability and dimensional stability for our tire. On the rubber compounding side, we have to bring together all these different raw materials or ingredients, mix them together into a homogeneous rubber sample, and test those physical properties for a specific design target. The base of every formulation is our rubber or our polymer. We have to work with either styrene butadiene, polybutadiene, or other synthetic rubbers that we make in the lab, or work on our natural rubbers, which come from the latex of specific trees. So depending on which application we're looking into, we have, for example, our passenger tire, which is a cross section here. You can see all the different layers and components. Each of these components is a different formulation or different compound. For a passenger tire, you can have up to 15 different formulations. And each formula has a specific purpose. So whether you're trying to improve your cornering, your fuel efficiency, your wet stopping distance, things like that, will change your formulation. So a typical product that I would normally get is if I were to be given either a new raw material or a new raw material source, I would have to develop the formulation for that. So I would work in our labs downstairs to design a formula on a small scale. So maybe 3 to 6 pounds of material. Test those properties for modulus, tensile, cracking, ozone, different things like that. Once I have selected a specific formula, I would put it into manufacturing, again, at a smaller scale. So I'm only mixing in manufacturing maybe 1 to 3 pounds, or 1 to 3,000 pounds, of material. And we would test that again to see if the manufacturing side of things can meet that design target that I saw on that small scale. Once we have done that and we have proven the actual feasibility of it, we actually build a tire. So once we build the tire, we have to test it either on a track or a drum to make sure that whatever tire performance or tire performance metric that we're looking into is either improved or stays the same so that the customer is happy or satisfied with whatever tires we put into the market. And so that's kind of the gist of what I do for materials engineering. It's a really cool job, and I work with a lot of different people from tire design groups, research groups, manufacturing, procurement, quality, just engineers from all around the world, really. But please consider materials engineering and boiler up.
Okay, so let me go back to presentation. You can see the presentation again.
Yes.
Thank you. Okay, so what do you do, like nuts and bolts about classes and how you move into materials? So in sophomore year, we have 5 required materials courses. There's kind of the big course intro. That's, and when I say big course, you know, that's 500 students a year take that. We have 1 lab course, MSc 235, and then we have 3 lectures, 250, 260, and 270. And they're taught, all courses are taught in fall and spring, so you can mix and match your courses. The only thing is, you really, in materials, you want to take that 230 course in the fall. You don't take that after you take the other courses. Junior year, we have 7 MSE required courses, 2 significant labs, one on materials characterization and one on materials processing. And we have 5 lecture courses. And the labs in MSE 340 are both semesters. The other courses are either only fall or only spring. And they don't necessarily need to be taken in order, but you do have to be aware that you can't necessarily take them whenever you feel like. Senior year, we have 3 required MSE courses. One is a lecture and then a year-long senior design where you and your team work on industry-funded projects. We also then require 6 technical electives, generally drawn from materials, but not exclusively, plus your gen ed type courses, okay? If you're interested, you can look at the MSE website and you can get the course sequence there. Okay, now, if you want more information about MSE, your group is in 131 right now, I believe. If you're still looking in the fall, you can take MSE 190. It's a 1 credit hour course, meets at 3:30. It's about cool things going on in materials right now. And it might, be it's things materials people think are cool. So you may or may not think so, but we all think they are. For advising questions, Vicki Klein, longest serving advisor in the college, is available via email. She's working 100% remotely right now, so you'd want to talk to her via email or phone, and she can help get you started if you have questions about that. But the real place where you may have questions, I think that students can provide a lot of input in that. So the goal of this was for me to spend about half the time talking and give you about half the time to talk to students. So I'd be happy to take any kind of big picture questions, but if you have anything specific, I'm going to turn you over to our capable team of 6 MSE undergraduate advisors or ambassadors who can do breakout rooms to answer your questions. So any big picture questions here? Okay, that resounding silence tells me that you're just all getting ready to think about, ooh, what questions might I have for our undergraduates? So if I can, I'll introduce the MSE ambassadors here. So Megan, give a wave, Trevor, Nicole, Ethan, Adam, and Luke. Okay. So they are going to be available for answering questions, telling you about, what a day in the life of an MSE student is like. Feel free to ask them about things like internship experiences, or how's it been this past year having labs that you have to do in groups of 3, or how annoying is your senior project if you can't come into labs as much? And by the way, Megan, how's the hardness?
We'll talk about it.
Okay, that's not good. So with that, I'm going to go ahead and let you guys do the breakout rooms. And if you have any questions, you can also email me, dfbar@purdue.edu. And I'll turn it back to Andrew for moving you to other rooms. Okay?
Again, if you have an iPhone, you should just be able to scan it. If you have Android, you'll probably need to download an app, but I've also been told that if you have Snapchat, you can scan the QR code with that as well. If you have any issues, just leave your name and Purdue email in the chat for me, and I'll log your attendance.